Okay, so welcome to the University of Paderborn. This is an introductory course on quantum computation. It's aimed at the master's level for a computer science audience. Okay, so as you can tell, I'm sitting in my lovely basement, which you are welcome to join me in. Like many schools around the world, we are currently doing an online semester, at least for now. The lectures will be in video form. And with that said, I'm going to try and keep it as much like it would be in a classroom as possible, in the sense that I'm going to be writing stuff on a board with a pen and just following my course notes as I go along. These are available on the course website, which we'll get to in a second. Okay, so for today's lecture, basically what we'll do is we'll start with some logistics. I'll show you the course website and the structure of the course roughly, and then we will start with our review of linear algebra. Okay, so but before we do that, let me start with a quote, which I think is one of my favorite for starting off any discussion about quantum computation, which is, again, this is on top of lecture one's notes. It goes, "I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed that the moon exists only when I look at it." Okay, so what does it mean? How could an object exist only when we look at it, right? So this course is going to be about using the principles of a set of physical laws known as quantum mechanics to do computation, right? And quantum mechanics is notorious for being highly non-intuitive, okay? We still don't understand what these mathematical laws mean, how to interpret them, because they're so at odds with our everyday experiences, okay? But nevertheless, the math seems to work. All of our gadgets around us are evidence of that, conclusive evidence of that. And now the question is, can we use these laws to compute? Okay, so let me be very clear. We're not physicists here. We're doing computer science, so we're not going to be doing much actual physics in this course. So we're going to see in lecture 2 that we're going to put down some mathematical laws that describe quantum mechanics as far as we're concerned, and then we're just going to work with those laws. Okay, so how you actually implement those laws in a physical system, that's beyond the scope of this course. Okay, so let me just, very briefly say, that quantum computing has been around for longer than you might expect. So actually, the first hint of quantum information comes from the late 70s, where Stephen Wiesner suggested this idea of using quantum states to come up with an unforgeable notion of money called quantum money. Okay, and in the 1990s, Peter Shor came up with this algorithm for factoring, this quantum algorithm for factoring that was polynomial time, and that's really what I think put the field into the limelight, right? Suddenly, it gathered a lot of interest. Okay, and here we are today. I guess it's been 2 decades since that, a bit over 2.5 decades since Peter Shor's work, and the field is actually really, really active now. And there are all sorts of exciting things happening nowadays for example, some of you may have heard of, this quest for quantum supremacy, if you will, where we as a field are trying to come up with short-term experiments that actually conclusively beat the best classical computers at some task. Okay, so there's a lot of money and time being devoted to the field now, and I think it's a really exciting time to be learning about it. Okay. So that's all I want to say about an intro. Let's quickly do some logistics. Let's go to the course website. Okay, so this is the course website, and you can just get to it by going to Google and putting in my name, say Intro to Quantum Computation. Hopefully it should come up. And sorry, this is the announcement page. And so, of course, you can ignore this information, so the lecture times, of course, we'll try and roughly adhere to that. I'll try and release a video coinciding with each of these lecture times. Likewise for tutorials. Classroom is obviously not important right now. In terms of a textbook, if you want to follow a textbook, like I said, in this course I'm going to be releasing course notes, some of which will be mine, some of which will be written by other people. But the standard text in the field for at least 20 years now has been Nielsen and Chuang, basically, and you're welcome to go get yourself a copy of that. In terms of the exam for the course, I was thinking doing oral exams because it'll be easiest. We could just do it via Skype, of course, one-on-one. But we'll see how that goes. A lot more people ended up registering than I expected. So hopefully we can handle that logistically. My office is this, although I'm not in my office nowadays, so you can forget about office hours. But what I've done is I've set up a discussion group on Panda. So for those at University of Paderborn, of course, you know what Panda is. On that news group, you could ask any questions you might have that other students might be able to answer, or myself. If you have, of course, a more direct matter to me, you're welcome to email me at this address here. Okay, so and some private details, which you're welcome to go follow if you like. In the meantime, the important tabs here for you are announcements down here, of course. We will go to syllabus and reading. Okay, so this is where I'm going to post the course notes every week. So as you can see, there's lecture 1 linear algebra review here, originally intended, of course, for April 6th. The semester's been delayed, of course. So if I click on this, for example, it should download this thing, linear algebra review 3, and there you go. Okay, so now you can see, so this should be roughly the format of the course notes. Okay, so I'll just leave that over there. The syllabus for the course is over here. Maybe before I do that, let me mention that, you know, if you would like some alternate reading, you know, here are 2 excellent sources. One is the set of more recent, let's say, lecture notes by Ronald DeWolf, which is, I think, an excellent set, covers a lot of material. The other is those by John Watrous, who is also a very well-known teacher and excellent at producing notes. So you can also go have a look there. In terms of syllabus, let's just download this. Okay, so all right, there you go. So here's the syllabus. Okay, so as I said, this is a master's course, as you know. Prerequisites, you don't need a background in quantum mechanics, but a background in linear algebra is more or less required. If you're really weak in linear algebra, I really recommend that you spend some time to work hard and get up to speed, because otherwise, it's like reading a book in English, right? If you don't understand English, you're not going to be able to read the book, right? And it's the same for quantum computing. Linear algebra is the language you're going to need. Okay, so that's why I'm really trying to make a serious point here. The class website is also listed here. Of course, that's a bit of a circular thing because you had to know the class website to download the syllabus in the first place. The major topics we'll cover are roughly speaking here. You know, we might deviate from this slightly, but of course we'll start with basics like quantum mechanics. We'll talk about things like entanglement, algorithms, error correcting codes, and so forth. So I think fairly standard fare for an intro to quantum course. The grading scheme in the German system, you know, this is kind of how I'll go between percentages to grade points. In terms of homeworks, we will only grade the homeworks for completion, not for correctness. Okay, so the idea is that, again, we're going to treat you like big boys and girls, and that you're going to take care of yourselves. So I'll, of course, release the solutions to each homework, and then you can see what you did right and wrong. I do have this in bold, which is that, you know, I really want to make sure that you guys do the homeworks after all, because otherwise you'll have difficulty really learning the material. Life lesson 101, right? If you're learning something complicated, do the exercises. Okay, if you don't do the exercises, you might think you understand, but odds are you really don't. Okay, and you know, everybody learns this. That's part of the learning process. Okay, so you need to do at least 50% of the homeworks to write the final exam. Okay, so that's this Studienleistung. Okay. Okay, and finally, to encourage you to do more homeworks, of course, the more the better, naturally. You know, this is how bonuses will work. Okay, so if you do at least 60%, we'll give you 1-step bonus, so your grade will go from 1,3 to 1,0, for example. Okay. So if you have any questions, of course, just post them to the discussion board on Panda or email me. Preferably always go to Panda first, because somebody else might have the same question, and so it'll just save myself a lot of time. But in the worst case, of course, you can email me. So that's all I really want to say about this course. Obviously, I think it goes without saying that, you know, please don't plagiarize. We don't take these things lightly at all, not at this institution, not at any institution, basically, of higher learning. So, you know, always write solutions yourselves. And you're more than welcome to discuss with friends and collaborators. You know, most things you do in real life that are difficult, you're going to have to collaborate on. So we do want to encourage those skills, but ultimately everybody should be writing up their own solutions, okay, that they get submitted. So back to the course website quickly. Up here, there's an assignments tab. You can click on it. So normally assignments will be due Fridays. In tutorial, I mean, that would be in person. So instead, I'm going to have to figure out whether we want to do this through Panda or just emailing me directly. And like I said, we're only going to grade for completeness. And we will discuss them in the next tutorial, the solutions. Okay. Obviously, you shouldn't be prepared to discuss your solutions because we can't do that right now in person. That's it. Okay, so that's the course webpage. If you have any more questions about it, again, post to the Panda group. And secondly, email me. Otherwise, I think we can begin the content for today's lecture. We're in about 11 minutes, so I'll try and go the usual time for a Monday lecture, which should be about an hour and a half now. So for this, I'm going to return to lecture notes. Okay. And so that means we're going to go to this thing. Okay, so yay fun. I'm going to have to write on this thing for an hour now. Hopefully it'll turn out all right. So let's begin. I said this is going to be a course on theoretical computer science. And what does that mean? Well, it means rigor and it means math, right? Okay, so we're going to be doing a lot of both. There will be an emphasis on things like proofs and formally modeling things mathematically. Okay, and we need this. Think about it this way, the stuff we do today in terms of linear algebra, it's kind of like learning the guitar, right? In the beginning, you have to learn the notes and do the scales, and like it really sucks, right? It's really boring. But that's the language you need to learn in order to actually get better and then really have some fun on the guitar, right? Playing some really great songs. And the same thing is true for any technical field. And here, the skills we need to pick up first are linear algebra, which again, I'm assuming you know to some extent. We're just going to be reviewing it. Okay, so let's begin. So just basic notation, right? Throughout the course, I'm going to be using 4 symbols over and over again, right? Complex numbers, real numbers, integers, and natural numbers. So the ones you probably see the most often are going to be the complex numbers, which we'll review briefly today, and the natural numbers. And it doesn't really matter. We can define the natural numbers as starting at 0 or 1. One piece of notation. Let me define. If I write this square bracket, by the way, this dots and an equal sign I'm going to use to mean a definition. So this is always going to mean the set of natural numbers from 1 up to m. Okay? Okay, and here, of course, m is a positive integer. So m is in integers, positive. Okay, so the basic objects we're going to be working with are going to be complex vectors, okay? Because it turns out these things are going to model quantum states. So when I write this kind of thing, so the Greek letter psi is going to equal to a vector. It's going to have some components, psi1 up to psi d, okay? And this thing is d dimensions, right? So the entries here are over the complex field, and here we have dimension d in this example, because I have d entries here. Okay, so each of the psi i's are in complex numbers. So let me very briefly review complex numbers, and especially in their 2 forms. Okay, so remember that complex numbers can be written in 2 forms. Okay, so 2 forms. Okay, so the first form is in some sense kind of like the old school way, which you probably saw first when you studied complex numbers, or maybe you haven't seen complex numbers before, and that's fine. That's why I take a bit of time to do this here. So typically, if I have a complex number C in the set C, can be written like this, right? C equals to A plus IB. And here, A and B are both real numbers. Okay, and I here is the square root of -1, right? So we define I as this thing over here. Okay, it's basically like a field extension. Okay, so the real numbers don't have a square root of -1, so we just add it as a new element, and you get the complex numbers when you do this. Okay, so that's the first form, and of course the second form is something called the polar form, and the polar form is actually a lot more useful in most contexts, at least in quantum information. Okay, so I can always write any complex number c as c equals to r times e to the I theta. Okay, and here, again, r and theta are going to be real numbers. Okay, and this is called the polar form. Sorry, let me be clear. So this is the polar form, right? And why do we like the polar form? Well, the polar form has this really nice geometric interpretation, which will come in really handy very often. And the interpretation goes like this, right? So if I draw, oh, clearly I'm not very good at drawing. This is why I didn't end up in art. If this is the real line, and here I have +1, -1, maybe here and here I have I and minus I, right? Then in this plane, we can very easily represent complex numbers. And how do we do this? Well, if I have, let's see, let me try and be a bit more advanced here. I could rotate this thing. Okay, so, ooh, very nice. Okay, so if we do this thing, so I can have a complex number here at this point, for example, right? And so what do r and theta mean in this picture? Well, r is just, it's nothing other than this, the length of this vector. Okay, and what's theta? Well, theta is just this angle with the x-axis. Okay, so it's a very nice geometric interpretation. This would be my point C, and technically speaking, well, in my notes here I have this point should be cos theta sine theta, which somehow doesn't seem right because it doesn't depend on r. So maybe there's a typo in the notes that I need to fix. Okay, but the key point that I need you to take away from this discussion here is just that r is the length of this vector and theta is the angle this thing makes. Okay. Okay, so for example, let's do some quick examples just to make sure we're comfortable. So if you want to have the number 1, right? The number 1, well, what is that? Well, the number 1 is right here, right? 1 is this guy right here. Okay, so in terms of polar form, what is it? Well, you know, the length of 1 is, of course, 1. So it's 1, r is 1. This is my r, right? And then this is times e to the I, and the angle here is 0 degrees, right? So it's times 0. And of course, e raised to the 0 is 1. So you just get 1. I mean, that's exactly what you expect, right? And of course, if you want to get I, then instead if we do I, which is here on the y-axis, then the length of y, you know, I haven't really told you this, but the length of I is 1, and so r is 1. And now what is the angle of rotation? Well, the angle of rotation is basically pi over 2, right? It's 90 degrees. So this is pi over 2, and so e to the I pi over 2 is equal to I. Okay, and one way to see this, if you don't want to look at this picture, is you can go look at, you know, Google Wikipedia and look up Euler's formula for e to the I theta and how it breaks down. So maybe this is just worth knowing in general. Sorry, let's not do it this way. E to the I theta is equal to, what's the order? Is it cos theta plus I sine theta? Okay, so yes, so this thing here is Euler's formula, which, you know, if you're ever kind of confused about how to think about e to the I theta, well, you know, technically you could always rewrite it this way. Okay, so this converts between the two forms for you. Okay, so so I is equal to e to the I pi over 2, and now I think is a good time to pause for a second and ask yourself, you know, we usually think of I as the square root of -1, so that, you know, I squared equals to -1, but the truth is that there's actually more than one right? If you look at this picture, there's actually more than one square root of -1, okay? And so one of them is I by definition, right? It's this guy over here, and, you know, how do we see that? Well, what did we say? We said that I here is a rotation here of pi over 2, right? And by definition, if you square that, if you do it twice, right, then you get, oops, let's not do that. Then you get -1. Okay, so I squared is -1 as expected. But there's actually another choice of number as well, which will have the same effect, and that is if you instead if you make your angle not pi over 2, but if you make it 3 pi over 2, right? So this number here, right, is -I, right? If you think about it, if you square -I, you'll also get -1, right? Because if I do a second rotation by 3 pi over 2, I also land on -1. Okay, so in that sense, e to the I 3 pi over 2 is also, this thing squared is also equal to -1. Okay, so we could have equivalently defined it this way if we wanted to, this notion of I, or the square root of -1. Okay, in terms of complex numbers, the complex conjugate, maybe I'll do definitions in blue. The complex conjugate of a complex number, whoops. So the easiest way to define it is if I have C equals to A plus BI, right, in the first representation, then the complex conjugate is defined as C star is equal to A minus BI. Okay, so note the minus sign, of course. And in polar form, it's also just as nice. So if I had C equals to R e to the I theta, then this gets mapped to C star equals to R e to, well, think about it for a second. What do you think should happen here? So the complex conjugate, what it does is it hits I with a -1. That's the way the operation works. And so where does I show up in the polar form? Well, it only shows up in this exponent. So what happens is that, and maybe I'll do this time, let's fix that in red, and here I'll do a minus I theta. Okay, so that's the complex conjugate of C written in polar form. Okay, so that's my brief detour into complex numbers for you. I'll do one exercise in a second. We'll be talking about complex numbers throughout this course, so if you haven't seen them before, that's completely fine. But do certainly spend a bit of time just thinking about them, okay? And again, the exercises for week 1 will help you do that. Okay, so what did I want to say? Just a brief note. So over here, you have this funny notation for a vector, which you'd never see in a normal linear algebra text, and that's because it comes from physics. I just want to mention this is called Dirac notation. Okay. And it's very convenient when you're doing things like computations, because you can put kind of whatever label you want inside this bracket. Not everybody likes it. I like it. Tough. Everybody has their own opinion on this. I think it works well in the context of quantum computation. Okay, so let's just do a quick exercise. Okay, so what is the exercise? This is the first exercise I have listed in the lecture notes. And what does the exercise say? Because there's no tutorial for the first week, so I'll do some of the exercises here in the actual lecture. Let's talk about the length or the size or the magnitude of a complex number. Okay, so what is the magnitude of a complex number C in this space, right? So to answer this, you should always go back to what you've learned before, right? How did we define magnitude for a real number? Well, if I had a real number that could be positive or negative, right? The notion of magnitude was given by the absolute value, right? And then this for sure is going to be in R plus. It's a positive real number. Okay, so we want to define some analogous notion for complex numbers. So how can we define the absolute value R? So, well, one way, a mathematical formula to actually get R is what? Well, you can do this, right? You can take your number, absolute value of R. You can take R, and then of course you could square it to get rid of the minus sign, and then take a square root. And by definition, that will give you the magnitude of R. It'll get rid of the sign. Okay, and we want to do the same thing for a complex number. And so if now C is in complex numbers, you might be tempted to do the analogous thing like this, right? And there's a tiny problem. The tiny problem is, well, if you want to think about it for a second, you can pause this video and think about it. But if you're done thinking, The tiny problem is that c squared, if c is complex, c squared is not necessarily real. Okay, and the magnitude of something should of course be a real number, at least intuitively. And so the fix here is that we need to get rid of this. So the fix here is that we need to do c times c star. Okay, so if you do 2 times c times c star, you'll see that this becomes a real number. Sorry, a non-negative real number more accurately, and then you can take the square root. Okay, so this is, by the way, equivalent to saying that this is true, right? So just something that will get used throughout the course. Okay, so let's just do a quick aside. Why in the world should this be true? Well, keep in mind that if I have a complex number c, then if you do the exercise, this is going to be twice the real part of c, right? Because it's going to essentially kill off the complex part. And well, c times c star, if you... okay, and by the way, the best way to see this is you actually don't want to work in the polar form, right? Just do this in the old school form. Okay, so if you take the product, what you'll see is that this should equal to... let's see, let's work it out quickly. A plus bi times a minus bi, right? And so what is this? Well, this is just a squared minus aib plus aib, so the inside cancels, of course. And then you're going to get plus b squared. Well, okay, you're going to get minus, let me be very precise, minus b squared, right, times I squared. But I squared is just minus 1. Okay, so you get a squared plus b squared. Okay, and that, of course, is a non-negative real number. Okay, now it makes sense then to take a square root. Okay, so these two formulas, by the way, are extremely useful to keep in mind. We'll see them kind of over and over again in the course. Okay, so what does that mean? So now we can talk about, let's apply this to the polar form. Now with the polar form, we could really easily see, I claimed that in the polar form that, if I had this complex number here, that the magnitude of that number was basically r, right? It's the length of this vector. And now let's just do a sanity check. Let's just make sure, of course, that the formula we came up with reproduces this complex number. Sorry, this value of r. So if I do this thing, the absolute value, right? I just plug in the formula. That's going to be the square root of r e to the I theta, right? And now I need to multiply by the complex conjugate of c, right? So I'll get this thing. And so what do I get? Well, I get the square root. You'll get r squared. And here, of course, you'll get, for the very first time, I'll do this explicitly. Of course, you just add exponents, right? These are just scalars. Okay. So you just add exponents. Of course, theta minus theta goes to 0. And so you get r squared times e to the I 0. And remember that, of course, e raised to the power 0 is, of course, just 1. So you get square root of r squared. And that, by definition, is just absolute value of r. Okay? Okay, so, and normally we think of r as, we define r as being a non-negative real number anyway, because it's supposed to denote a length of this thing. Because without loss of generality, of course, the sign could be hidden in this rotation angle theta. Okay, but so you see the magnitude of this thing is just r, okay, as I claimed. Okay, good. So that is our review of complex numbers. And so that, like I said, the reason why we care about complex vectors is because they're going to be used to represent quantum states. Okay, so for this reason, let's just remind ourselves how you play with complex vectors just a little bit. So I already defined this notion of psi equals to, psi 1 up to psi d as being some complex vector now in CD. And so now hopefully you should be a bit more comfortable when I say this thing has complex entries. And so this is, by the way, what we call a ket vector. Okay, and let me be clear. This is a column vector, right? It is downwards. And we can take the conjugate transpose of this thing. This is the first operation. So let's talk about the conjugate transpose. Conjugate transpose. Okay, and what is the conjugate transpose? Well, technically speaking, what you do is you take the star. Okay, and when you take the star of a vector, it's the way we define it is you take the star of each of the, it's entry-wise, of each of the entries one by one. Okay, and then you take the transpose of the full thing. And the transpose, I haven't defined it in these notes, I think, but I'm just going to assume you kind of know this from basic linear algebra, right? It just flips the matrix, or the vector in this case, about its diagonal. Okay, and note the transpose doesn't need a square matrix to be defined. Okay, so formally though, let me just write, if I had psi over here, right, then on the right-hand side, this thing here, and the notation, by the way, we use for this is we just put the bracket backwards. Okay, and the funny name now we gave to this is a bra. So it's bra psi. And what is this really? This is just going to be psi 1 star, psi 2 star, dot, 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 psi d star. Okay, so you'll notice two things happened. The first thing is that, I'm taking the stars of each of the entries, so the conjugate complex conjugate. And the other thing is I've taken the transpose of the vector, so it's switched it from being a column vector now to a row vector. Okay, so you might be wondering why in the world we have these silly names like ket and bra. And it's because it's probably some physicist's idea of a sick joke, which is that if I want to take an inner product now, which we'll do shortly, we'll see that an inner product will write like this in the end. And then you could call this thing a bracket or just a bracket for short. Okay, so we'll get to that in a second. Okay, and so having defined this bra operator, okay, I can actually define the inner product now. And I don't need to actually define anything in some sense because it's already given already. So let me write inner product here. Okay, so what is the inner product? The inner product of two vectors, it's going to be defined like this. So you have two vectors, psi and phi, right? The inner product, this is the notation we use. It's just given by this formula where you sum over all the entries. Okay, and keep in mind that, this thing is just a column vector where the entries are phi. So here we go, phi. And this thing, remember, we defined it as a row vector with the stars on the entries. So now you have psi I. But there's a star. Okay, so if you just multiply, this row vector on the left with this column vector on the right, and just do your standard matrix multiplication rules, you'll get literally this formula out. Okay, so there's no real additional definition I had to throw in here. It's just the product of these two vectors. Okay. Okay, and again, this is called a bracket sometimes. And let me be clear, just some properties. So note, one thing that's very, very useful to keep in mind is that if I want to swap the order of the two vectors in here, like if I want to do this, okay, I can't just do that in general, I have to add a star. Okay, and of course keep in mind that this thing is a scalar, right? It's an element of the complex numbers, and so then it's completely well defined for me to take a star operation here. You're just taking the star of a complex number. Okay, and why do we like the inner product function? Well, it gives us a notion of length. Okay, so let me just take a very brief detour to remind you of this. If you imagine you had, this axis, right? And we take, say, two vectors, right? One vector is maybe just the x-axis, right? To keep life simple. The other vector will be this thing over here. Okay, so maybe let's just define these guys as psi and phi, right? And this is just an R2, right? What is the inner product between these two visually? What does it measure? Well, it's a measure of the overlap of these two vectors. Okay, so what do I mean by that? It basically means that if you take this first vector and you kind of project it down onto the second, it's the length of this distance here, okay? So it's trying to understand how close these two things are. And of course, if the two vectors, if these are really the same vector lying on top of one another, then you'd really have a very long projection, right? And so this gives you a notion of how similar two vectors are. And we're going to use that in a second. But first, let me mention that now that I have a notion of overlap, right, I can define a notion of length, basically how long is a vector. And what I do is I basically take the overlap of vector with itself. Okay, so I can define in particular this thing, which I'll give a fancy name, the Euclidean norm, which you've already probably seen in high school. Maybe you didn't call it this. And well, how do we figure out the length of this thing? Well, think about complex numbers, right? When we talked about the length of a complex number, what was the formula? We did CC star, right? We took the number, its complex conjugate, and then we took a square root. You can do the exact same thing with a vector. Okay, so you take the vector psi, you take its complex conjugate, which for a vector, remember, meant its conjugate transpose, so the bra vector. This is an inner product function, so the output is a complex output in general, of course, will be a complex number, but in this case, we're taking the inner product of a vector with itself. So here, the vector, you can prove that this overlap will always be a non-negative real number. And then, of course, it makes sense to take a square root. So that is going to be the 2 norm of an arbitrary vector psi. Take the inner product with itself, okay, and then take the square root to get rid of the square, basically. Okay, so let's just do a quick sanity check exercise at this point. Okay, so let's imagine my vector psi looks like this. It's 1 over square root 2. This normalization factor will come up quite often. Okay, so you'll notice that, take a moment, think about this. What space does this live in? So this is in C2, right? A 2-dimensional complex space. And now we want to know, well, first let's do, what is psi? Well, remember what we do is we take the transpose of the vector. So first of all, the constant in front doesn't change in this case, it's a real number. And so we're going to write 1 in I. And the next thing we have to do is take the complex conjugate entry-wise. And so the complex conjugate of I is minus I. Okay, so that's bra psi. And now that I know that, I can compute, therefore, the Euclidean norm of psi. Okay. And by the way, you might be wondering why there's a 2 in this base, and there is a reason for it. You can generalize this to more general formulas where they're called the Schatten P norms, basically, where if you put another number here, well, there's a slightly different formula. But, we won't go into that just yet. Maybe we'll see it later. But the point is that, the 2 is meaningful to put here. Okay, it actually stands for something. Okay, so what is this? Remember, this is just the square root of psi, overlap of psi with itself. Let's just compute that. So on the left here, I have bra psi, which is the square root of 1 over root 2 I 1 minus I. And on the right, I have times 1 over root 2, right, times 1 in I. Here it is. Okay, I guess I technically didn't need that extra bracket there. It will be hard for me to erase in any clean sense. Maybe I could fix that. You don't do that. No, don't do that either. Okay, forget about it. Okay, so what happens here is we have the 1 over root 2 squared is a half, of course. So that's going to just come out and you'll get 1 over root 2 again. Okay, and then I'm going to have this inner product, right? So what is this inner product? Well, it's 1 times 1, right? Square root of 1 plus minus I times I. Okay, and what is this thing? Well, I squared is minus 1, but there's a minus 1 here, so this is just going to be 1 over root 2 times root 2, which just equals to 1. Okay, so in other words, this is what we call a unit vector. The norm of this vector is precisely 1. Okay, and what does that mean? That means that if you look at it in terms of this complex plane, right, in terms of this thing, seems to have started writing bigger. In terms of this complex plane, right, it just means that the length of your vector is 1, right? It lies on something called the unit circle, okay, which is a circle you can draw of radius 1. Okay. So that is the Euclidean norm. And now that we have a notion of norm, okay, or the size of a vector, we can define a notion of distance. And distance is, of course, super important. So So defining, maybe I should stop writing so big and zoom in a bit. Defining distance via the Euclidean norm. And by the way, this formula is fairly general in the sense that for any norm, the Euclidean norm is just one of an infinite number of norms. For any norm, you could once you have a norm, you could always define a distance, right? And so the distance between so the distance, whenever I write b/w, that means between. The distance between two vectors psi and phi. They do have to live in the same space because we're going to subtract them. And sorry, let me be very clear. We're talking, in this case, it's the Euclidean distance because it's going to be based on the Euclidean norm. It's just going to be the norm of psi minus phi. Right, and so, this is just a vector in CD. Oops, it should go like this, right? CD. And clean that up properly. Don't always get an undo function in life, so now that I have one, I want to use it properly. So this is just a vector in CD, so it makes perfect sense to plug in this absolute value, norm function. And what does this mean? Well, this just basically means that if we do an example, if we had the two vectors again, here's one vector, maybe I should do it in a different color. Okay, intuitively, what is this going for? If you had these two vectors, psi and phi, well, if I take psi and I add minus phi to it, that means I have to add this vector, but in the opposite direction, right? So the new vector I get will look something like this, right? Again, I'm terrible at drawing. Please don't hold it against me. Okay, so this is psi minus phi. And then, so that's the difference. And then, of course, the 2 norm is now trying to understand the size or the length of this vector. Okay, and so the reason why this is important, of course, is because if we're saying that two quantum states are represented by complex vectors, well then, how well we can distinguish two quantum states via a measurement in experiment is going to depend, of course, on how close two states are, right? If you have two states that are very, very close in, say, the Euclidean norm, then it's intuitively going to be very difficult to distinguish these two, right? Just like when you have two real numbers, right, that are very, very close, maybe they agree on the first, like 100 bits, right? It's very hard to distinguish these. You really have to go very far down to the 101st bit before you can distinguish them. And, that's just a very rough analogy. In the quantum setting, this is also going to be true. You're going to have to do many, many experiments in some sense to distinguish vectors which are very, very close. Okay? Okay, so why do we like, well, okay, let me just state maybe two properties of the Euclidean norm. Okay, maybe I'll do this also in red. Okay, so the first one is positive scalability. And all that means is that if I take the norm of a vector psi times some complex number a, then that a just pops out and we take the absolute value of it. Okay, so this is for a in the complex numbers, is exactly what you might expect. And by the way, you should really think about these norms as just being higher dimensional generalizations of just the absolute value function, right? Because the absolute value function has a similar property. If we just think about the absolute value on real numbers, if I were to take the absolute value of a times b for two real numbers a and b, that just equals to the absolute value of a times the absolute value of b. Okay, and norms are generalizing this to higher dimensional objects. So let me just delete that. All right. Okay, and the second one is the triangle inequality, right? This is one of the simplest and yet most useful statements in mathematics, certainly in linear algebra. Okay, and what this says is that, for all, when I do the upside down A, remember this means for all states psi and phi, which live in some space CD, right? What this says is that if I take the norm of this thing, right, that norm is always upper bounded by the norm of the first vector plus the norm of the second vector. Maybe I could just, the nice thing about this is that I'm technically not limited in space. Okay. So, what does this mean? So the triangle inequality is something you use every single day of your life, I can almost guarantee you. So anytime you're walking on campus and you're going on a path which goes around a patch of grass, you almost certainly do not take the path you cut along the grass, right? And then the grass dies in that shortcut. And that's exactly what the triangle inequality is saying, that if I have two vectors, so here are my axes, so I'll have a vector psi, right? And here's my vector, well, technically I'll just draw the other vector here. Here's my vector phi, right? This guy over here. Then what is the sum of those two vectors, right? Well, the sum of those two vectors is just this thing, right? It's just this vector here, psi plus phi. And all this thing is really saying, the triangle inequality, says that, of course, the direct route from this point to this point is always shorter than, these detours you could take along these other vectors. That's all it's saying. Okay? So, the world as we know it functions this way, at least at the level at which we see things in this, like, 2D projection that we live in, essentially, right? Okay? And using these two, you can prove, it follows that for all vectors psi, what good is a notion of size if it's not always non-negative, right? It would be very odd. And indeed, for all psi, you can prove using these two that the norm of any vector psi you come up with, that's always non-negative. Okay, so just a sanity check. Okay, so that's all I want to say about vectors, norms, and distances. So the next thing I want to remind you about are orthonormal bases. Okay, so let's see how this thing is going. Let's see, we are going down and to the right. Let's try and stay somewhat stable and keep writing in a similar fashion. Okay, so maybe I'll write here. So now we're talking about, oops, let's not do it in red. Orthonormal bases. Okay. So remember that for any vector space you work in, like let's say CD, there's always a basis you could use to represent vectors in that space, right? So this is kind of like saying, if you want to write a book, then it doesn't really matter whether you write it in, say, English or in, say, German. At the end of the day, both languages can represent more or less the same story, right? It's just a matter of which perspective you want to use, right? And the same thing happens in linear algebra. You can use different sets of bases, if you will, to represent the vectors you're interested in. Okay, so in particular, for this, we're going to need what? Well, we'll need two definitions here. I'm going to need to remind you that if I have a set of vectors psi I goes from 1 up to, well, let me not use that just yet. Let me just say this is a subset of CD is orthogonal. Okay, what does that mean? It means that for all I not equal to j, if I take the inner product of the two vectors, psi I and psi j, then that's 0. Okay, so what does this mean in terms of geometry? Like, what does the picture look like? Remember, two vectors are orthogonal if they basically look like this, right? If, roughly speaking, they have a 90-degree angle, right? That's the way you should think about it, at least in 2D. Okay, and so that's an orthogonal set. Okay, and more generally, we'll say that the set is not just orthogonal, we'll say that it's orthonormal. So this is going to be even stronger. It's orthogonal But I'm going to ask something stronger. So here I just said that if I is not equal to j, if you take the inner product of two different vectors, you get 0. Now I want to say something stronger, which is that the inner product is always either 0 or 1. Oh, sorry. I need to get rid of this now, actually. Oops. So now it's just for all I and j. I'm going to get rid of this constraint, psi I and psi j. This thing is going to equal to something called the Kronecker delta of I and j. Okay, so this is going to show up over and over again. Let me just briefly define it. I forget if there's an ES here. Kronecker delta. Okay, and what does this thing do? It's just a very simple function. It's defined like this. Okay, so this thing is either going to be 1 if I equals to j, or it's 0 if I is not equal to j. That's all the Kronecker delta function says. So in words, we say, remember, a set of vectors is orthonormal if I take the inner product or the dot product of two vectors in that set. If I take the inner product of one vector with itself, the norm is 1. So everything is basically a unit vector in the set. And second, if the set is orthogonal. So if I take the inner product of two different vectors, they're always at a 90-degree angle. The inner product always goes to 0. Okay, so that's going to be an orthonormal set. And you can think of, these basis vectors are kind of like a reference frame for your space. All right. And remember that, from basic linear algebra, we know that if you want to come up with a basis set for a d-dimensional space, it's necessary and sufficient to use d vectors. Okay, and in particular, if you have d dimensions and you want all your vectors to be orthogonal, you can only come up with d at most. Now, in this course, there's going to be one particular basis, which of course we'll use over and over again, and it's more or less the basis in which classical computation takes place, at least the way we'll think about it. And that's going to be the so-called computational basis, or standard basis. So as I was growing up, I would call this the computational basis, but now I prefer, just the more common, maybe, at least among the linear algebraists, this notation of a standard basis is just easier to say, it's shorter. Okay, so what is the standard basis? So for C2, right, or more generally, well, okay, let's start with C2 in this case. This is what? This is just going to be, the two basis vectors 1, 0 and 0, 1, right? So assuming you've done linear algebra, you've almost certainly seen this basis before. You just didn't know we called it the computational basis. And intuitively, you should think of this as representing bit 0, this basis vector, and bit 1. Okay, that's ultimately where this is going to go. And you'll notice that this thing is an orthonormal basis. So if you were to look at the norms of these vectors and their inner products, they would satisfy the conditions you required of an orthonormal basis. Okay. And I'm not going to verify here that this is an orthonormal basis. Just believe me or believe your teacher who taught you linear algebra. If I think of, I could write, of course, any vector. The point of an orthonormal basis, or of a basis in general, is that any psi in the space now can be written in terms of these two basis vectors, right? In terms of this reference frame. So alpha 0 plus beta 1. Okay, you could always write it in this way, and if you want me to be very precise, one of the hardest things of getting into quantum is not quantum itself, but it's just the notation, right? I mean, dealing with these funny bras and cats can be kind of funny. So in the beginning, I'll sometimes try and write out the explicit vectors and matrices until you get the hang of it. Okay, so I can always write any vector in this space relative to this basis, right? And we'll say the vector is, of course, normalized if this thing has length 1, okay? But the nice thing is that let's just see what happens, right? So normalized. If the 2 norm of psi is equal to 1? Okay, so it's a unit vector. And using this formalism in the standard basis, we could see exactly what this means if I write my vector in the standard basis, then we could do this most generally, which is the following. Remember, this is just the, whoops, let me not do this. Psi 2, right? This is just the square root, psi, right? The inner product with itself, square root. And then what you do is you take the square root, and now I do, remember that this is what? This is going to be, okay, so what is the bra of this thing, right? The ket of that thing is just alpha 0 plus beta 1, right? That's what this thing is. That's this ket vector over here. The bra vector is just the same thing, right? Except we have to take an alpha star, and this thing is going to go to bra 0, beta star 1. Okay, so you could verify that if you're not comfortable with that, you could verify this. Just plug in the definition of the bra vector. Okay, so if we work out this expression now, what do we get? Well, you know, we have 4 terms. We're going to get alpha star alpha. Okay, and then I'm going to get the inner product of 0 and 0 plus alpha star beta inner product 0, 1 plus alpha beta star 1, 0. And finally, beta star 1, 1. Okay, this is all under the square root. Okay, so let's just simplify this. So now it's very important for you to remember earlier on this identity that if you see a complex number alpha times its complex conjugate, so in this case it's alpha star alpha, that always equals that complex number, the absolute value of that complex number squared. Okay, this identity is going to come up over and over again. So it simplifies things to just write that. Right, so that's just by definition of the absolute value on complex numbers. The inner product of 0 with itself, well, we said that this is an orthonormal basis, so this inner product is just 1. It's a unit vector. And what about these cross terms? Well, over here, I have the inner product of 0 and 1. These are orthogonal vectors, right? So this inner product is 0. It's likewise here. So the cross terms die off. The only thing left here is going to be this term here. Again, the inner product of 1 with itself is 1. And then I'll get beta star. Remember, this just equals to this thing. So just to jog your memory, remember this just meant that absolute value of alpha squared is equal to alpha star was how we define this absolute value function. Okay, so a lot of times, especially when we move to larger dimensional systems, typically in quantum computation, part of what gives quantum computers their power is that you can work in this very large dimensional Hilbert space or the vector space, and then you certainly don't want to just write out these giant vectors and do these inner products. That's just ridiculous, right? So instead, it makes a lot more sense to work in this Dirac notation, because you can just manipulate terms a lot cleaner, basically, without actually having to write down the full vectors. And that's one of the first things I'm going to encourage you to do in this course, which is try and always avoid writing out full vectors and matrices whenever you can. See if you could just do it directly in Dirac notation. Okay, and let me clarify that, of course, this definition of, I gave you the standard basis for C2, but of course you could generalize this to CD, and then you would just have, 0 is just going to be, you have a 1 in the very first position. 1 is then you put a 1 in the second position. 0 is everywhere else, ... And the very last one will have, sorry, I should maybe do this. The very last vector will have 0s everywhere and a 1 in the last position. And you'll notice that all these vectors aren't CD. And you might be wondering why in the world I labeled this last vector by d minus 1 as opposed to d. There are d vectors in total, and the reason is because I started counting at 0, right? That's why. So it's a zero-based counting system. And that's partly because we want to generalize this idea of classical bits being 0 and 1. So we start counting the first base vector at 0 rather than 1. Okay. So that is the notion of vectors, okay? Of orthonormal bases, right? And so now that I've told you about vectors and how to think about vectors in terms of lengths and representing them, now, of course, vectors are not so interesting unless you could do things to them, right? You want to apply some sort of maps. And that's going to be the next thing we'll talk about, which are linear maps. Okay. Okay. Now, you can think about any map, of course, you could in principle define. Like, so given a vector of psi, I could make up whatever I want. Maybe psi will get mapped to the 0 vector for all psi, for example. Right? That's an example of a map. So in this course, in quantum mechanics in particular, the types of maps we're going to allow are so-called linear maps. Okay, so that's why I wrote linear here. And so what does this mean? This means the following. This means that, and so this definition is the definition of a linear map you should remember throughout this course. Okay, so this property will come in useful multiple times, and we'll even use this to represent maps that don't look like maps on vectors. They can always be rephrased that way. Linear will always mean the same property I'm about to write down. Okay, so if I have a map phi, right, and the map takes you from one space to another space, so in this case, for concreteness, I'm just assuming you're going from CD to CD, but the input and output spaces don't have to match, of course, right? So we're going to say that this thing is linear if for any vector psi, which lives in, well, maybe I shouldn't write it this way. Maybe I should write it if I have an arbitrary, okay, maybe I will just write it that way. For all psi equals to, and I write it as a sum of terms. It doesn't really matter how many terms I have. There's some complex coefficients here and some vectors. What happens when I apply the map to a sum of vectors, right? What is that? Well, that's just equal to the sum over I of alpha I psi I, right? And the key point of being linear is this inequality, which I'll highlight in red. That the sum comes out. Okay, and so do the constants. And you might as well just apply, so it kind of commutes with the linear operations, with sums, for example, okay? Okay. Well, I should be careful when I say linear operations, sums of vectors, okay? So you're not allowed to add constants, for example. Okay, so that's going to be the definition of a linear map, okay, that we'll use throughout this course, because quantum mechanics is going to be based on linear maps. And more generally, the set of linear maps from two spaces, so maybe I have some space to y, okay? So the way I'll denote this is just going to be denoted this way. So I'll put in a squiggly L, x to y. Okay, so in this course, we're going to be formal. We're going to explicitly state our input and output spaces because that's what good people do, okay, because then it's easy to follow. Okay, and a lot of time for brevity, we might say, if I really have the same input and output spaces, I might just write L of x. Okay, and so that just means maps that go from x to x. Okay, so let me really kind of work with this definition with an exercise, because I really want to drill home this idea, right, of what does it mean to be a linear map, right? This linear property is really what we care about. Eventually, we're going to write these things as matrices, but the key point is this linear property. That's what we're looking at. Okay, so consider a linear map phi, which goes from C2 to C2, right? And what is the action of this map? Well, I'm going to define it so that on the first standard basis state, it goes to 1. On the second standard basis state, it goes back to the first one, back to 0. Okay? And so intuitively, you might already, if you're thinking in the classical world, I mean, look at this map. This is a linear map I defined in terms of vectors. But if you kind of forget the ket notation, you might already recognize what this map is supposed to model, right? What is this doing? It's just flipping bit 0 to bit 1, at least at a logical level. So in some sense, this is going to end up being the quantum NOT gate. Okay, but we'll get to that, of course. But more generally, let me just say that if I were now to take phi, I've specified the action of the map on a basis, right, on the orthonormal standard basis. Now if I were to take that map, therefore, on any vector in the space, which can be written, of course, as 0 plus beta 1, by linearity, right, the nice thing is that now, what is this? Well, it's just this, right? It's just beta times 1. Okay? And so here I didn't know what to do with this, right? Because I have no idea how the map acts on this funny input. But I do know how the map acts on the individual basis vectors. And linearity tells me that that's all I need to know, basically. So now I could just plug in my definition, right? Phi of 0 takes us to 1. It flips the 0 to a 1. And phi flips this 1 to a 0. Okay, so that's the action of this map on the state. Okay, and so this in particular teaches us a very, very important lesson, which will hopefully stay with you throughout this course, which is that if you want to know the action of a linear map, like fully characterize it, I mean, in principle, you could plug in any vector. There's an uncountably infinite number of inputs you could plug into this map, right? You're working over C2 in this case. But you only need to specify the action of the map on one fixed basis. Pick your favorite basis, specify the action on that basis, and by linearity, that tells you everything you need to know for any input you could ever plug in. Okay? Now, why is that important? Well, that's important because it allows us to write the map now in terms of a matrix. Okay, so this is just a map right now. I just told you, and the most general definition of a map is you tell me the input-output behavior. You know, you say on input this, you get output this, right? So that's one way to do it, like via a lookup table. But there are different ways you could represent these maps, right? And the most natural representation, which you've certainly seen before, is via a matrix. Okay. Okay, so let me just say over here, representation of linear maps via matrices. Okay, ta-da. Okay, so what does that mean? Well, maybe the easiest way maybe the way I'll represent or I'll introduce is let me kind of work a little bit backwards, right? So if I specify, the action of this map on every single basis vector, I could write these things in a big list, right? All, you know, the input on 0, what is the output? You know, like this guy here, and this one, I could write those side by side, right? So let's suppose I have, so take a linear map, doesn't matter which one, take an arbitrary linear map, phi, right? And this thing takes you from CD to CD. Okay, and you can generalize this, of course, but because the input and output spaces are the same in my example, I'm going to end up getting a square matrix in the end. Okay, and what I could do is, remember, I could specify the action of this map fully by just looking at its action on a basis of my choice, and I'm going to choose the standard basis. Okay, it doesn't have to be that way, of course. So consider this thing here, right? If I take first the action on standard basis vector 0, and let me be clear, you know, again, I'm thinking of 0 as being, you know, this big vector which is d-dimensional, right? So there are d terms here, not just 2. Okay, so if I take this thing, like what is this thing? This is going to be a vector, right? And I can then look at the action on 1, the action on 2, and so forth, right? Up to the action on the last basis vector for the space, standard base vector is d minus 1. Okay, each of these things is going to be, let me be very clear. So each of these things is going to be a vector, right? So this is just going to be some d-dimensional vector. This is some d-dimensional vector, and so forth, right? This is some d-dimensional vector. And, you know, if you do the naive thing of just sticking these things together, right, from left to right, just cramming them together into one big block of numbers, right, what you're going to get is a matrix by definition, right? So I can take this thing. Now the way I'll do that, if I just concatenate these vectors one next to each other, right, then what I'll get is a matrix, right? And let me call this matrix, I guess, A to be consistent with my notes. This is a matrix A. And the idea here is going to be what? That what are the dimensions of this matrix? Well, the height of this thing, the number of rows in the matrix, is D by definition. And what is the number of columns of this matrix? Well, there are D vectors here, right? There are I started with a D standard basis states, so there are D columns. So this is going to be a D by D matrix. Okay. So that's kind of how I kind of went backwards in this presentation. That's how matrices come about. Okay, in terms of if you start thinking about linear maps. Okay, and remember, it's because we were able to use this property that because the map is linear, to specify its action on anything in the entire space, it suffices to just tell me its action on a fixed basis of your choice. So, of course, in this representation of the map, this matrix A specifies the action of the map phi. This is written relative to the standard basis, right? But of course, I could have plugged in another choice of basis. And then I would have said that, A would be the representation of the map relative to that other basis, right? Not relative to the standard basis. So you could always write, the point is you could always write the same linear map relative to any different basis. The infinitely different many bases there are, each of them will give you a different representation of the exact same map. Okay, so more formally, let's see if we wanted to say, what is this thing over here? A D by D complex matrix A. Matrix A. What is it really? It's just going to be it's a two-dimensional array of complex numbers. Is a 2D array of complex numbers. And the ijth entry of this thing, so this is row I, column J. That entry there is just going to be some complex number. Okay, so for example, if I look at row ij, that means that you go down I and then you go to the jth column, basically, right? And then you look up the number there. And so that's basically it. And for there is a one-to-one mapping, right, between matrices and linear maps, right? So for every linear map, there's some underlying matrix and vice versa. So in this course, we'll kind of use that equivalence interchangeably. So if I say linear map, I might as well say matrix and vice versa if you like. Sometimes it's easier to use one language than the other. So let's do an example to highlight this exercise. Okay, so what is the 2 by 2 matrix? Okay, so from the previous exercise, we had this map, right? So we talked about this quantum NOT gate in the previous thing, which we said that, this equals to 1. And so let's continue. So let's write the map from the previous exercises in its matrix form. Okay, and again, remember the idea is that this was supposed to specify, I kind of gave away that it's supposed to be a quantum NOT gate, basically, because it logically flips 0 to 1 and 1 to 0. So let's see what the corresponding matrix should look like. Okay, so here I've just reminded you what the action of this map was. And remember the idea here is what? Well, all I do is if I want to write down the matrix form of this map, right, I say A equals to what? Well, I just list as columns phi of 0, right, dot, 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 phi of 1. Okay, and what is that? Well, that is just by definition, we said, well, this is the column vector 1, and this is the column vector 0. Right? And in this particular case, remember that we are working in C2. Yeah? Okay, and then let me just write out the definitions of those vectors, right? So what are those vectors? Well, ket vector 0 is 0, 1. Ket vector 1, 0, 1. Ket vector 0 is 1, 0. Okay, so that is what we will end up calling the quantum NOT gate, and it often takes this label of x. Okay, it's the x gate. Okay, we'll come back to this later. Okay, but the point is that, this is the very easy and straightforward way that you could take the action of a map on a basis and just write it out as a matrix. Okay, and similarly, we can do another exercise which states that, so let's go in the opposite direction. So suppose I'm going to give you a matrix and I want to know what is the linear map this thing is representing. What is the linear map represented by the matrix 1, 0, 0, 1. And here I'll put an identity here. I'll put the I, because this is called the identity matrix, right, if you'll remember. So let's just go backwards now. So I can extract from this what's the action of this map on these basis vectors, right? So remember that essentially the first column of this thing is going to be the action. Oh, maybe I should not write it this way. The first column of this thing is going to be equal, seriously. All right. The first column of this thing is, whatever the map phi is that we're looking for, it's the action of on 0, right? And remember that this is the action of phi on the base vector 1, right? And so what is this thing really doing? What we conclude is that phi of 0, what is phi of 0? Well, this first column is phi of 0, and that's just, 0, right? It hasn't done anything. And likewise, what is phi of 1? That's the second column, and that is still ket1, the vector ket1 by definition. So what is this map doing? This map is not doing anything, right? It's just mapping 0 back to 0 and 1 back to 1. So this is the identity map, and in terms of its specification as an action on a basis, you could always write it this way. Okay. Now, of course, a lovely topic which any discussion of linear algebra has to mention, which is matrix multiplication. I'm just going to state the definition here. I'm going to assume you've done this before. Remember, the definition is kind of technical, but once you get the hang of it, it's not so bad. So the product of, the product AB, I should say, of matrices, D by D matrices, A and B. Okay, so how can we specify these things? Well, we could either say, for example, some people might write, the complex numbers and D by D, for example, because you can think of this as this is indexing, this is the first component, the row component, this is the column component, right? We could also think of this as these guys are linear maps, of course, which act on CD. Okay, well, remember this was my short form for saying that this is a linear map taking CD back to itself. Okay, so this is the forma, the notation I'll tend to use in this course. Okay, and remember that the product of these two things is nothing other than this formula. The entry ij of the product, okay, we can only do it this way, is going to be the sum over k equals to 1 up to d of ak, aik, b, k, comma, j. Okay, so that's just the formula. I mean, I expect you to have seen this before. If you've forgotten, that's fine. You could just play with it a bit more. Let me make a very, very, very special comment. Okay, special comment. Okay, so in the world of real numbers that you know and love, right? Integers. The order of multiplication does not matter, right? Multiplication is commutative. Not true for matrices. Okay? So unlike for, say, complex numbers, right? It is not true in general. Of course, for some matrices it is true, but it's not true in general that for all A, B in this space, AB equals to BA. So this is not. So in general, this is not true. Okay, of course there are there are cases where this does hold. For example, diagonal matrices. If you have two matrices which are diagonal on the same basis, then of course they will commute. But in general, this does not hold. Okay, and I don't want to say too much about this, but I do want to mention that this is actually very, very important. So it's not just oh, it's just the mathematics. It turns out that the very nature of the world around us really depends on the fact that matrix multiplication is non-commutative. Okay, so I don't claim expertise on this topic by any means, but if you dig up some physics lecture notes, you'll see that the reason why like electrons don't crash into the proton of an atom and just kind of the atom doesn't self-implode is because of this, or at least partly because of this fact that matrix multiplication is not commutative. Okay, so do keep that in mind. It's a very ugly kind of thing that things don't commute, but it turns out that our world really requires this. Okay, so other properties now of vector spaces, or of maps I should say, are we could talk about, so I have a map. Okay, sorry, let me do an example here. So let's define, the X matrix we already defined this way. And another very well-known matrix in quantum computation will be this one. It's almost the identity, but I'm going to put a -1 over here on this last coordinate. Okay, this is called the Pauli Z matrix. Again, we'll see these again later. And I'll let you verify on your own, okay, that x times z is not equal to z times x. Okay, and very briefly, the notation you might use for this is something called the commutator. Okay, so we'll see this notation again later in the course, but you might define this bracket as xz minus zx, right? And in this case, therefore, if the x and z commute, basically, then this commutator goes to 0, right? But of course, in this case, this is false. I'm telling you that x and z don't commute, and therefore this is not true, right? Their difference is not 0. So this bracket, this commutator, is not 0. Okay. So now that we're talking about linear maps, right, and matrices and matrix multiplication, now you might start to want to understand, what are the properties of the maps themselves, right? So we know its action, but for example, how big is its output space? Okay, and for that we need to be formal about what we mean about what it means to be big or small, etc. Okay. So let's define the image of a map first. So think about the output of a map, like all the possible outputs, as an image. Right, and in principle, the notion of an image of a map doesn't need a linear map, but of course, in this course we're talking about linear maps. So the image of, when I say linear maps, again, I could equivalently write a matrix, and that's what I'm going to do. So the image of a map is just going to be the set of all possible outputs that this thing could produce. Okay, so if you think of it as, there's some input space here, right? And then there's some mapping that takes place. Let's say the map A, right? The question is, what is this map able to produce here, right? That's going to be the image. And now we should be clear, of course, well, let me not say too much more than write down the formal definition of the image. It's going to be basically, how do we formally specify this? Well, it's going to be the set of all points here, right, in this output space where there was somebody that you could have applied A to, so that you could have gone forward into this point. Okay, so that's how we're going to formally define the image of A. It's everybody basically who had a so-called pre-image under A. Okay, that's this point here. Okay. So let me just write down a formal definition. It's a set of all vectors psi in CD such that psi equals to A times phi for some phi in CD. Okay, so in this picture, right, let's be very clear. In this picture over here, this one here is going to be my psi. So this set is a set of all output vectors psi over here, such that, there was some pre-image phi I could have started with and shoved phi through the map to get back to psi. Okay, and that's what this phi is. There's some phi that was the pre-image. Okay, so that's the image. It's essentially it's the output space of this map, or the set of output vectors. And of course, this output space is it's a vector space, and so we could talk about its dimension. And so the rank of A, right, is what? It's just going to be the dimension of the image of A. Okay, so A is a vector space. I mean, it's not difficult to argue that, if you have two vectors which are in the image of A, then so is any linear combination, for example. Then the rank of A, since it's a vector space, the image of A, you can take its dimension. You could figure out what its dimension is. That's what this is here. And that's what we call the rank of A. Okay? And so, again, this is just, I'm really just thinking of A here as a linear map here, even though I wrote it as a matrix. It's just a dimension of some output space, right? Okay, so let's do a quick example. So if I have, for example, and whenever you have a new concept you're learning, always remember that you always want to check the boundary cases, right, to make sure you really understand this. So remember, A is a map that takes me from a d-dimensional space to d-dimensional space. And if I say, for example, that suppose the rank of A is D, okay, then what kind of map is A, right? Or what is the image of A more generally, right? Then what is the image of A? Well, the image of A is d dimensions, right? It's basically the full space, okay? So in this case, the image of A is really all of CD, okay? Okay, and now in this context, we can define the null space of this map, which is kind of the complement of the image, if you will. Okay, so the null space is going to be what? Well, it's the set of all vectors that this map will basically kill. It's going to send them all to the scalar 0. Okay? So more formally, this is going to be the null space of A. Okay, maybe I should write this like this. So I'll write null of A. What is that equal to? Well, it equals to the set of all vectors psi in CD, such that when I hit this thing with the map, it goes to 0. Okay, so that's the null space of the map A. And the nice thing about the null space is that there's this nice rank nullity theorem, which states the following, always good to remember, which is that if I take the dimension of the image of A, right? Remember, this is just the rank of A by definition, plus if I take the dimension of the null space of A, okay, that just equals to the full dimension D, like the entire space. Okay, so in this sense, the entire space is either going to be in the image of this map or it's going to get killed by this map. Those are the two options. Okay. So maybe next let me talk about matrix operations. Okay, by which I mean we've talked about operations on vectors, and now we can generalize these to matrices basically. Well, okay, maybe before I do this, I guess I'm pausing because I do want to maybe do this exercise. So let's go back and do this exercise. So here's an example for rank. Oops. Seriously. There you go. So here's a matrix B, right? And I'm going to write it like this. And now we can think about what, let's say, what is the null space of this matrix B, right? So what is the null space of B, right? What is the set of all vectors that get sent to 0? And, the most naive way to figure this out, at least in this easy example, is you can just take B and multiply by, some arbitrary state, right? Let's multiply by some arbitrary alpha 0 plus beta 1, right? And I'll even write it in matrix form because it's a small example. I know I'm violating my guidance to you not to do things in matrix form, but for this very basic example to demonstrate, what happens? Well, we're going to have alpha basically plus alpha 1 plus beta 0, and then this row is 0, so you're just going to get 0. Okay, so what does this mean? This means that no matter which input vector you give me, it kills off the second coordinate, right? So who are going to be the vectors that go to 0 under this map? Who gets killed off completely? Well, these are the guys who have alpha equal to 0, right? If alpha is already 0, then your output is always going to be the 0 vector. Okay, so what is the null space? The null space is just going to be what? It's going to be the span, basically, of, well, technically it's going to be the span of 1, 0, right? Right, it's going to be all, it's basically ket 1, and then you can multiply by whatever scalar alpha you want. Oh, sorry, did I want to do this the other way? Sorry, that's the image. All right, I'll get back to that in a second. So, whoops, null space is the span of everything of this form, right? Because the map kills off the second coordinate, so you'll always end up with a 0 vector. Okay, and so this guy over here, this is of course not the null space, it's the image. So the image is the set of all vectors, basically all vectors of this form with 1 up to some scalar, right? Those are the guys that can possibly come out of this map. Okay, so what is the rank of the null, the dimension of the null space, right? The dimension of this is just 1. Why is it 1? Well, it's the span of one vector, right? So it's a one-dimensional space. And same with the image. It's the span of one vector. So this is also going to be a one-dimensional space. Okay. And just like this rank nullity theorem up here said, if I sum these two guys, I should get the dimension. So if I sum the null space dimension 1 plus the image dimension 1, then I get a sum of 2. And that is the local dimension 2, right? It's a two-dimensional vector. Okay. Okay, and in this way, of course, what is the rank of B? Remember, the rank of B is nothing other than the dimension of the image, right? So it's really just 1. Okay, so there's only a one-dimensional space here kind of that comes out of this map. Okay, so now I could talk about matrix operations. Now I feel better, right? I can go to bed at night, sleep well. Matrix operations. Okay. So again, we define this notion of a ket vector, a bra vector, and we can generalize these notions to matrices. These are all going to be linear maps that we'll need. So 3 linear maps. I remember linear meant that you can apply this map to linear combinations of objects, and the definition will just act linearly. So 3 linear maps we're going to need are the following. So I'm going to use a star to denote the complex conjugate, the transpose, which we've already more or less touched on, and the dagger. Okay, and the dagger is just going to be the combination of these two. This is what we used earlier to go from a ket vector to a bra vector. And these guys are just going to be exactly what you think. So this is going to be entry-wise. A is a matrix here, let me be clear. Entry-wise complex conjugate. This is going to be the transpose. Okay, and this is just the dagger. is what we call it. Okay, or the Hermitian conjugate, for example. Okay, and a star, we'll just define it entry-wise because it's well, like I wrote here, it's defined entry-wise. So a star of ij is nothing other than a of ij. Pull out the entry at that position and then take the complex conjugate of that. Same here. The transpose can be defined entry-wise. All you do is just swap the indices, right? So you'll notice the order of the j and the I just changed. And if you combine them, the order doesn't matter. You get the so-called dagger operation, also called the adjoint. Okay. Okay, so let me make a note here in terms of properties, that if I take AB transpose, right, that just equals to, you can verify this yourself, B transpose A transpose. And in particular, that means that because the adjoint also takes a transpose in there, it's hiding a transpose, you have the same property for the dagger. Ta-da. Okay, and we've already seen this before, but these operations, the matrices you apply them to don't have to be square, right? They could even be shaped so that one of the dimensions is 1 and you really just have a column vector, right? That's also, a column vector is an example of a matrix, right? Or vice versa. You can also think about it in the other direction. So so let me make another note that I could do the same thing. If I take psi and I take its dagger, right, it's going to literally produce the bra vector, right? That was the definition we gave earlier. Okay, and this adjoint operation is going to play an absolutely crucial role in this course. Okay, so it's going to give us basically the inverse of quantum operations, for example. So maybe let's do an example here. What is the adjoint? If I define A, for example, well, okay, maybe, okay, we'll get there later. Let's do it this way. 1, 2, 3, e to the I pi over 2. Okay, so what is the adjoint of this matrix as an easy exercise? Well, we have to do two things, right? We first have to take the transpose, and that means that, these diagonal terms have to swap places. And then we have to take the entry-wise complex conjugate of each entry. And the only non-real expression in the matrix here is this bottom right term. Otherwise, everybody will stay the same, right? So let's first swap the places of the off-diagonal elements. So there goes the 3 and the 2. And now let's take complex conjugates of all the entries. 3 and 2 are real, so there's nothing to do. Same with 1. And now this one, I'm going to put a minus, because that's what it meant in polar form to take the complex conjugate. Okay, so that's those are 3 linear maps which are super useful. Okay, so here's, maybe I'll label this as 1. Maybe I'll just go like this, and I'll label this thing as 1. Now let me label this thing as 2. What is this thing? Now we're going to talk about the trace. Yes, the trace. How could we forget the trace? Okay, so what is the trace? The trace is also a linear map. Okay, and we define it this way. We abbreviated just TR. And what it's going to do is it's going to take your favorite vector, for example, or matrix, and it's just going to squish it down into just one number. Okay. So most generally, I'm going to define it in this way. I'm going to define it as the input is a linear operator acting on CD, which remember means essentially a D by D matrix. And it's going to squish it down into just one number. Okay, that's the trace map. And what does it do? It's going to be very simple. It's just going to add the terms on the diagonal of this matrix. So if I have this matrix here, it's just going to be adding, these terms here. And it just throws everything else out. Okay, so the formula is, if you give me the trace of A, it's going to be the sum over I equals to 1 up to D, so 1 per dimension. And it's just going to sum A of I comma I. Okay, so these are the diagonal entries of the matrix. Okay, so the trace turns out also to play a crucial role in quantum information. Here are some properties. Well, actually, okay, there's really only one property, so scratch that. And the main property is this fact that it's so-called cyclic. Okay, so remember I told you that matrix multiplication is not commutative, and there's really nothing we can do about this as far as the world works in some sense, right? But if you take the trace, you can kind of bypass this in some sense. And so what is the cyclic property saying? It says basically the following, that if I take the product of any three matrices, trace of ABC, then I can just cycle things around. If I want, I can bring this A to the end. So only, the first one can only go to the end. So let me just write down the formula, and then you could apply the formula in any way you like, of course. Okay, so this is the formula, and based on this, you can do what you like. And so as a special case, of course, this means that if I just have two matrices, AB, this equals the trace of BA. Yeah. So even if AB is not equal to BA. Okay, so the trace is cyclic. It doesn't care about the order of multiplication. This is very, very important. Okay, and I won't work it out here, but previously we showed, well, we didn't show, but I asked you to show basically that xz is not equal to zx, right? I said that these two don't commute, but show that since you've already in theory, of course, worked out xz and zx as I asked you to, show me that the trace of zx actually equal to the trace of xz. Okay. Okay. Let's see, how are we doing here? Okay, so let's continue about, talking now about representations of matrices, and in particular, using like these operations like the dagger, the adjoint, we can write down a very, very useful representation called the outer product representation. Okay, so we already talked about the inner product. Okay, recall, let's just do an aside here. So recall the inner product. Okay, so here, if I just had two vectors psi and phi, the inner product I wrote this way. This was a well-defined operation because this thing was, well, let me first write down this thing. This thing was d by 1, and this thing was 1 by d, right? So the inner dimensions match, and the matrix multiplication is well-defined. The output will be 1 by 1. Okay, but you're all scientists here, right? And so as a scientist, you should ask, okay, well, let me start tinkering with this thing and see what happens, right? So what happens if I instead write this? Oops, sorry. Let's get rid of this funny angle bracket. Okay. What happens if I write that? I write them in the opposite order. Is this even well defined? And, well, what is this? This is a column vector, so it's d by 1. This thing is a row vector, so it's 1 by d. And indeed, this thing is well defined, right? Because the inner dimensions match. So really, this is just multiplication of a column vector by a row vector. And the output will therefore be d by d, right? It's completely well defined. And this thing here is what we call the outer product of two vectors. And unlike an inner product, which takes you down to a complex number, the outer product kind of blows you up into a matrix. Okay, so you get something that's d by d now, instead of 1 by 1. So let me define this a bit more formally. So for any psi, phi in complex D, let's do this, the outer product is just going to be psi, phi, like this. And again, I'm assuming everything is just d by d here, so this is just going to be some d by d complex matrix. Okay, so let's just do some quick examples. So if I want to do, for example, 0, 0, right, the outer product of 0, 0, what is that? Well, the first guy is just this column vector. The second guy is just this row vector. And if you just do matrix multiplication, you'll see that what you'll get is, 1 times 1 is in the top left corner, 1 times 0 is in the top right, and so forth. And you'll just get this matrix back, which we did, I think, in one of the exercises. Okay. And instead, if I did, well, let's do something a bit suggestive, actually. If I do this now, what is this? Well, this is just, ket 0. And now I do bra1. So I just swap the 0 and the 1. And what do I get? Well, if you do the multiplication, you'll see that you'll get this. Okay. So again, put on your scientist thinking hat, right? And say, well, that's interesting, right? If I put in 0, 0, then I get a matrix which is zeros everywhere, but there's a 1 at position 0, 0 of the matrix, top first row, first column, basically. Here we're counting rows and columns starting at 0. And if I say 0, 1, well, then I get a 0 everywhere except in the top right of the matrix, which happens to be at index 0, row 0, column 1, which is exactly what this suggests. It's almost as if, this is the row index and this is the column index. Okay, and this is not a coincidence. Okay, so this is a very, very nice trick that you can use to work exclusively in Dirac notation and not have to switch back and forth into matrix notation. So let me write this out generally. If I write I comma j for, let me be clear, these guys are always the standard basis vectors in CD. So whenever I index a vector by, just like a number I or j, I typically mean the standard basis vector. Otherwise, I'd use something like a psi or something. So has a 1 at position I comma j, zeros elsewhere. Okay, so it's no coincidence. This is always what happens. Okay, so why in the world am I showing you this? Well, of course, this will have many uses later, but it gives us a very, very compact way of writing an arbitrary matrix. So I can write an arbitrary matrix this way. Okay, so what do I mean? I can write A. So take your favorite matrix, and what I'll do is remember that well, I have two sums. I have to sum over, well, okay, I have to start at 0 and d minus 1 technically. Okay, and at each entry of the matrix ij, if I index the rows and columns starting at 0, then what am I going to get? Well, you tell me first the entry at that position. And how do I insert it into the right slot? Well, what I do is I just want to put down a matrix which has a 1 only at position ij and 0s elsewhere. And that's nothing other than this thing, this outer product between standard basis vector I and standard basis vector j. Okay, so ta-da, A can be gigantic, but if you have a nice closed form expression for the entries of A, you could always write it in this very compact form. And let me show you something cool. Trust me, it's cool. It is cool. Which is that, what does this do as a result? If I take any matrix A that's written in the standard basis and I take a bracket around it with standard basis vectors, I claim that what this is going to do is it's just going to rip out a single entry of A, the entry at row I, column j. So how do we prove this? Well, using this outer product representation, it's going to be easy. So let's just do it, right? What is I? And let me use maybe a different notation here. S equals to 0 up to d minus 1. T equals to 0 up to d minus 1 of A, S, T, S, and T, and J, right? So here what I did is I just plugged in, of course, this outer product expansion. And what I like about this computation is that it's going to start getting you used to just playing with these bras and ket vectors, right? What are you allowed to do? What are you not allowed to do? Okay, so the inner product function, well, okay, here you have a sum, right? And we can bring the sum out. Okay, so let me just write both of these together for brevity. Okay, these are scalars, right? They come out. Okay, so we can bring out the sum and the scalars. And then what we can do is we can bring in the bra and the ket vector, right? And what we'll get is we'll get the inner product of I and S and T and J. Okay, And this just follows by the linearity of you know, these objects and these maps involved, basically. And oh yeah, okay. It's because, sorry, let me be a bit more formal. The inner product is linear in the second argument, this j, and it's, well, aj technically, and it's conjugate linear in the first one. So you have to be a bit careful, but in this case, it's completely fine. Okay, and so what is this? Well, you know, this thing is what? These are both standard basis vectors with potentially different labels. And remember, the standard basis is an orthonormal basis. So each of these is going to be a Kronecker delta that goes to 0 if these two indices mismatch, and if they match, it goes to 1. So in particular, what this means is that unless I equals to s, this term disappears, and unless t equals to j, this term disappears. And so what that means is that the only terms in this double sum that'll survive are the ones where s equals to I and t equals to j. So in particular, I don't have a sum at all. I just have one term when s equals to I and t equals to j. So as I claimed, when you take the bracket with I and j, for standard basis vectors I and j, it's just going to rip out entry ij of the matrix A when A is written, of course, relative to the standard basis. Okay, and this worked because we were dealing with this, well, not worked because, but we can prove it very easily using this nice outer product representation, this guy here, for any linear map. Whew. Okay, and so you might not like the way this looks, but you know, this thing is going to come up all the time when we talk about quantum measurement, so please get used to it, right? I mean, just take your time, stare at it, play with it, be happy. Okay, so let's do a sanity check, as always, right? Do the exercises. Okay, so remember that we wrote this X matrix as this thing here, right? So what is the outer product notation of this thing? Well, again, you know, to represent this thing, I could just use this fact, right? That if I want to have a matrix with just a 1 here and zeros everywhere else, well, you know, that just means I put a 0 here for the row in the outer product notation and a 1 for the j. So if you think about it a little bit, you'll see that this is nothing other than 0, 1, right? This gives you this guy over here, plus the 1 and the 0. Swap the two. You know, and you can see that, and that gives you, sorry, that gives you this one here, right? And of course, you know, this thing is just the dagger of this thing, right? You just take this thing and you transpose it into 1 pops here. Okay, so now we could ask, it's very easy to say, what is, say, 0, 0, x 0, 0, right? When we do things like measurements later, this kind of thing is going to show up all the time. And, you know, I don't want you to sit down and write out the matrix X and do this matrix vector multiplication. It's just silly. It's much easier if you just work in the outer product form. Okay, so what is the scalar? Notice how, again, one of the things you have to get used to with quantum information is just parsing these expressions, right? So what is this thing? Remember that this is a column vector. And, you know, this is just a d by d matrix. Well, okay, sorry, C2 in this case. And so you can think of this whole thing as a column vector, also in C2. And now you take the inner product with ket 0, or bra 0 more accurately, and you get squished down into just a scalar. Okay, but what I can do now is I could rewrite x in outer product form. And why is this nice? Well, because now I can do the same thing as before, right? I could rewrite this as 0. So of course we bring this in here and we bring this here, right? So you get 0, 0, 1, 1. Did I do this right? Oh, sorry, yes. Except that it should be 0 there. So not yes, but no. Okay, so 0 goes to 0, 1 goes against 0, plus 0 goes to 1, 0 goes to 0, right? That is 1 goes like this, 1 goes like this, right? That's this term, that's this term. Okay? And again, what is this? Well, you know, this is the inner product of 0 with itself, which is 1, but this is the inner product of two orthonormal basis vectors that goes to 0, right? And likewise, this is ket 0 inner product ket 1. We know that that's 0. And so the whole thing goes to 0. And so does this make sense? I said that if you squish x with bra 0, ket 0, you get 0. And remember, over here I told you this cool fact. You know, I hope by now you really believe me that it is cool, right? It's cool that 0, 0 of x, what it should do is it should rip out the top left corner, entry 0, row 0, column 0 of x. And if I look at x, well, row 0 is this, column 0 is this, it's this guy, right? It just ripped that out for us. Okay, so this outer product notation makes it very, very easy to evaluate expressions of this form, or of this form. Okay, and how about we write the trace using the outer product? And now if I write the trace of x, okay, the trace of x, I know what it is, right? It's the sum of the diagonal elements. So in particular, it's 0 plus 0, which is 0. But let's be formal. It's the trace of, again, let's write it in outer product notation. Okay, and the trace is a linear map. That means I could do this, right? I could write it as in terms of each sum individually. Again, why am I doing this exercise? Well, there's a very important lesson here, which is that, okay, so let me mark this, of course. Trace is linear. This is why you're allowed to do that. And now I have the trace of 0, 1, right? And the trace is cyclic, okay? And the trace is cyclic not just for, square matrices, right? I mean, you could do the same thing here. I could take this 1, for example, and I could move it. By cyclicity, I could move it to the other side. I'm allowed to do that, okay? The trace doesn't care if it's a lopsided matrix or like a D by D matrix. So in particular, I could write this. I could write the trace of 1 and 0 plus the trace of 0 and 1. Okay, and this is because trace is cyclic. Okay. And now what is, the inner product 1 and 0? Well, we know that this thing, right? Well, okay, so first of all, this is a scalar, right? It's the inner product of two vectors, it's a scalar. So, and the trace of a scalar is just going to be the scalar. I could throw the trace out because it's basically taking the trace of a 1 by 1 matrix, right? So I don't really need a trace at this point. I could equivalently just write this. And I could equivalently write this for the second term. And here, each of these is 0, right? Because it's just the inner product of 1 and 0, ket 1, ket 0, and these are orthogonal. Okay, so in this outer product form allows us to take very nice traces. Again, without writing out the matrix, I did not write out a matrix at any point in this computation. Okay, and for these small matrices like 2 by 2, you might not really care to do this, but when we start getting to like n qubits and things grow in terms of dimension 2 to the power n, like you're going to have to do this sort of ket-bra manipulation, direct notation manipulation. Okay, it's just not feasible to just write things out explicitly anymore. Okay, now last topic for the lecture. You ready? The last topic, I always enjoy teaching this topic in Germany because the name is the German word for the term, actually. Okay, eigenvalues and eigenvectors. Okay. Okay, so roughly speaking in German, eigen means own, right? It's going to be the matrices kind of own vectors and its own values, if you were to say it literally. Okay, so eigenvalues and eigenvectors are going to be absolutely fundamental to the study of quantum information, so let's just review them. This is probably something you studied in Intro to Linear Algebra and hated. Too bad. Okay, it's come back. And so what is an eigenvector? Given any matrix A, it's a linear matrix acting on CD, right? An eigenvector, and often in this course I will just write evec for short, as is fairly standard, is any non-zero. Okay, it's important. We make things well defined by making it non-zero, so it's interesting. Vector psi st. So when I say st, remember this means, or maybe not remember, but I'm defining it for the first time, such that. So I'll use this abbreviation throughout the course. So such that a psi is equal to lambda psi for some lambda in the complex numbers. Okay, so in this picture, this is the eigenvector, and this is the eigenvalue. Okay, what we call the eigenvalue corresponding to the eigenvector psi, and of course this is all relative to the matrix A. Okay, so in some sense this is the matrice's own vector, if you will, and there'll be a set of these, not just one. And we'll say more about this in a second. Okay, so the point here is that if I take the matrix psi and multiply by A, what happens is basically nothing. Psi stays the same up to scaling by some lambda. Okay, so let me be clear that it's not really nothing. It's actually quite interesting. It's not like an identity matrix. Okay, so let me be very clear. Because each different eigenvector will get scaled by a different value in the end. So let's do an exercise. Okay, exercise. So the claim is that two vectors, and I'm going to, part of this exercise, the point of it is to also just define these things. So from now on, whenever I write the plus state and the minus state, I'll mean these two very special vectors, which are special throughout quantum information, 0 and 1. So just the sum of those two, get 0 minus 1. Okay, and again, this is just an intro lecture, getting you used to these things. So let me write out the actual vectors. So this is, first standard basis vector plus the second one. And this is the same, except it subtracts the second one. So you get a minus coordinate here. These are the two vectors. And I claim these are both, for an eigenvalue, let me be clear, sometimes I'll just abbreviate this one eval. So both of these vectors are evex, or eigenvectors, of Pauli x. Okay, and let's just do a sanity check. If I do 0, 1, 1, 0 times 1 over root 2, 1, 1, right, times this thing. Well, the 1 over root 2 just comes to the front. It doesn't matter. So then I'll have 0, 1, 1, 0. 1, 1, right? And then what is this thing equal to? Well, it's just going to be equal to, 1 times 0 plus 1, and then 1 times 1 plus 0. So, whoops, let me not drop that. Well, that's the exact same thing. That's just the plus state again. I didn't lose anything, right? And, yeah, maybe I'll just, let's just see how this works in the bracket notation, in the outer product notation, because it's a good exercise. So alternatively, I could have rewritten this thing. I could have rewritten it like this, right? I could have written it as, in bracket notation, this was just this. That's this thing, right? And the plus state is just this, right? 1 over root 2, 0, plus 1 over root 2, 1, right? That's just coming from here, right? So, instead of writing things out as a matrix, I could just multiply it out. And of course, you'll get 4 terms in the expansion. And what will you get? You will get, well, let's just write it out like this. Oops. You will get, okay, so first you'll get 0, 1, 0, and then a 1 over root 2. So then you'll get, everything will have a 1 over root 2, so I'll just put it in brackets to make life easy. That's the first term. The second term is going to be a 0, 1, 1. Oops. And then the third term will be 1, 0, 0, plus 1, 0, 1. Okay, so not all these terms will survive, right? This one dies off because you have the inner product of 1 and 0. Likewise here. The only ones that are these guys, this one goes to 1. This one goes to 1. And so we get 1 over root 2, 0, plus 1. Okay, and that's just plus. So, bingo, no matrices required. Okay, so these are the two eigenvectors, and so what we've shown is that, x plus equals to plus. So the eigenvector is plus, and 1 is the eigenvalue, nothing happened, right? And I won't do it explicitly, but you can do the same thing, just multiply them out, and you'll see that minus is an eigenvector with value -1. Okay? And now that we know what eigenvectors and eigenvalues are, the reason why we're talking about these things is because in the world of quantum information, the types of matrices we see turn out to be very special in the sense that they can always be decomposed very, very nicely in terms of their eigenvectors and eigenvalues. And this is a fact, like anytime you do a proof in quantum information, the first thing you do is you try and apply this fact, okay, which is the spectral decomposition. So let me tell you what that is. Okay, spectral decomposition. Okay, so for any normal matrix, normal means something here. It doesn't matter too much at this point, and probably not too much in this course per se. Pretty much everything we see will be normal. So normal just means that A times A dagger equals to A dagger A. Okay, so the matrix commutes with its adjoint. Okay, so most matrices we see will be normal. Can always write for any normal matrix A, can write a okay, so let me be a little bit more precise here. Again, let me just assume that A is going to be for concreteness, it's just going to be a D by D matrix. Okay, it's a linear operator sending CD to itself. Can decompose A via its eigenvectors and eigenvalues. Okay, I could always write A equals to the sum, and A is a D by D matrix, and so you could come up with basically an orthonormal basis of eigenvectors, and it basically looks like this. Here are the eigenvalues of A. So this is going to be eigenvalues of A, one by one, and these are going to be the corresponding eigenvectors. And here you'll see the power of the Dirac notation, because I could just label, if I put this funny cat around it, now I'm talking about a vector, right? And so it's a very easy way for me to say, okay, here's the vector that corresponds to the eigenvalue. Okay, it's just a very easy labeling system. Okay, so these are the eigenvalues and the eigenvectors of A. Okay, and this is a remarkably useful representation of the matrix A. So it tells us basically everything we need to know about how A acts on the space. So let me tell you a bit more about that. Okay, so it turns out we can always choose. So this is not true for arbitrary linear operators, right? So every linear operator has at least one eigenvector, right? Sorry, at least one eigenvalue, I should say. But the eigenvectors are not necessarily always going to be orthonormal. But for the types of matrices we'll be considering, these normal matrices, you can always take the eigenvectors to be an orthonormal basis. So this gives us another way to get orthonormal bases beyond just the standard basis. Okay, so number one, so the evex, this lambda I, which is a set of vectors, right? This is some subset of CD, can be chosen, okay, without loss of generality. Okay, so if it's the first time I'm writing this, so let me define this. This means without loss of generality. Okay, that means that we could just assume this and we don't lose anything. To be, and here's another abbreviation I'll use. ON will stand for orthonormal. Basis for CD. Okay, so you can always choose the eigenvectors of A. From among the eigenvectors of A, you could always pick a set, basically, that forms an orthonormal basis for CD. Okay, so why is this useful? Okay, so therefore, any vector in the space psi in CD, if given any basis, you could write the vector relative to that basis, and in particular, you could write it relative to, the eigenvectors of A. Okay, can be written psi equals to the sum over I of alpha I lambda I, and these are just for some coefficients alpha I in the complex numbers. Okay, so this is really nice because if we want to know the action of this matrix A on an arbitrary vector psi, if you can write A in terms of its spectral decomposition like this, and you could write psi relative to that same basis, then, well, you know exactly how these terms behave with one another, right? The inner product of a lambda I here and a lambda j here, it's an orthonormal basis. So you know everything. The inner products are always 0 or 1. So it becomes very easy to analyze this. And let's see a place where we could use this. Okay, well, sorry, let me not do that just yet. Before I do that, I want to point out that the rank of the matrix A, where for the case of where A is normal, is just going to be the number of non-zero eigenvalues of A. Okay, so if you know the spectral decomposition, that already tells you what the rank is, the dimension of the image, remember? And finally, there's this very nice claim. If I take the trace of A, it has a very, very nice representation in terms of the eigenvalues of A. So it turns out to just be the sum over the lambda I equals 1 up to d. Okay, and the funny thing is that this is irrespective of the basis in which you choose to write A. Okay, so let's prove this claim. I told you there'll be proofs in this course, so let's prove this one. So the trace of A, what is it equal to? Well, here is an example where you want to use the spectral decomposition. Remember, when you're doing a proof, first thing that you should try, at least ask yourself if it might help, is the spectral decomposition. So it's the trace of sum over I of lambda I. Okay, so this is just spectral decomp of A, right? And now the trace is linear again, right? So that means I can move the sum out, right? And I could also move the scalars lambda I out, the eigenvalues, and instead do this. Okay, and that's awfully nice. And now I use the cyclicity of the trace, right? Oh, sorry, let me point out, of course, trace is linear again. And now I can use the cyclicity of the trace to bring, right, this bra around so that I get an inner product. All right, and once I have the scalar, I can just drop the trace altogether. So the trace is cyclic. Okay, this is what I get. And, well, this is just the inner product of eigenvector with itself. We're going to always assume, remember that the eigenvectors are chosen to be orthonormal. And so that means that these inner product of lambda I with itself is just 1. It's a unit vector. And so what you get is the sum over I, lambda I, as claimed. Right? That's exactly the expression I claimed. Okay, so using all this notation we've developed in the spectral decomposition, we can prove a very nice relationship between this linear map trace of A, which is going to be very important in this course, and the eigenvalues of the operator A. It's just the sum. So for example, if you look at another matrix quantity, which you might have seen before, the determinant of a matrix, it's also related to the eigenvalues. It turns out it's just a product of the eigenvalues. Okay. Okay. Now, quick exercise, sanity check. So remember that I already wrote down the eigenvectors and the eigenvalues of x. And now let's just write down the spectral decomposition using that. So recall we said that if I do x times the plus state, I get the plus state. If I do x times the minus state, I get the minus state. And therefore, let's just plug in the definition of the spectral decomposition. of x is what? Well, it's just going to be the eigenvalue plus 1 times the first eigenvector plus plus, and the second eigenvalue minus 1 times the second eigenvector. All right, so where was my spectral decomp? Well, okay, here's an example, right? It looks like this. It's a sum over eigenvalues times eigenvectors, right? And there it is. And if you just expand these guys out, so just take plus, expand the outer product, you'll see that this is exactly the matrix X. What? Okay, now, and so the rest of the lecture notes is a little bit about, how you compute the eigenvalues. So you might, normally what you do is you do this, right? Okay, I don't want to say too much about this because we won't use this in this course. Okay, so this is really just to remind you. So, where do the eigenvalues come from? You can't just make them up, right? The way we normally do this, right, is what you do is you compute the roots. Remember, compute the roots of the so-called degree D characteristic polynomial. And what is PA? Okay, so what I do is I take my matrix A and I say lambda I minus A. I want to figure out the roots of this. So this thing here is the determinant function. Remember, you define this as the determinant of A. So think back to your linear algebra course. This is just this funny formula. Aij times, well, okay, there are various ways to define this. I'm going to define it this way. And what is this funny matrix? A subscript ij, right? That's just, it's a submatrix of A where you throw out row I and column J. Okay, in particular, if you have the reason why I'm mentioning this is that, okay, so again, in this course, we're not going to use it too much. It's good to remember. So if you want to know what the eigenvalues of a matrix are, in theory, you could take your variable is lambda times identity minus your matrix. You put it into this determinant function. Out will pop a polynomial which has degree D. You need to find the roots of that polynomial, and those will be your eigenvalues. Okay. In particular, the determinant function for a 2x2 matrix is very nice, right? So if I just have a 2x2 matrix A, B, C, D, right, that's just equal to A times D minus B times C. Okay, so using this as an exercise, I'll leave it to you. What are the evals, the eigenvalues of the Z operator? 1, 0, 0, minus 1. Okay, and so you should be able to figure it out. For 2x2, it's very easy. The determinant is clean. But like I said, more generally, we won't actually go through the characteristic polynomial. A lot of times we'll be able to just guess the eigenvalues just by clever observations, if you will. Okay, last observation to close this lecture. Last observation. Okay, sometimes it's very difficult to figure out what the eigenvalues of a matrix are, and indeed, in general, the problem is complexity theoretically hard if the matrix is represented the right way. Okay, so should be careful. So if I have a D by D matrix and you have the whole thing explicitly written down, it's very easy to find all the eigenvalues, by which I mean it's in the complexity class P. We can do it in polynomial time, generally speaking. If the matrix A is not written in explicitly, but you have some sort of succinct representation for a really large matrix, then you can prove it's generally at least NP hard, even so-called quantum NP hard. But we won't get to that in this course. But the simple observation is that sometimes for some matrices, it's very easy to spot the eigenvalues. Okay, and so if you have a diagonal matrix, please do remember this. If you have a diagonal matrix, right, which means, you know, your numbers are just here, A, B, C, D, dot, 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 and everything else is just zeros, then the eigenvalues are just sitting on the diagonal. Hello. There you go. The eigenvalues are all your diagonal entries, it turns out. Okay? And in this case, the eigenvectors are just the standard basis. And so why am I mentioning this? Well, and the evex are the standard basis. Okay, so why is that true, by the way? Okay, so I want a vector, let's call this A. I want a vector A such that, a vector psi such that it will rip out this first eigenvalue A, right? How do I extract that? What do I choose? What vector? Well, here's another trick I'll teach you, which is common in, of course, the field. It's a great trick to learn at the beginning. And the trick is that if you want to extract out, say, the first column of a matrix, what you do is you multiply by the first standard basis vector. So pick psi is equal to 0. Okay? And what you'll find is that A of 0 is equal to little a of 0. Okay? And more generally, A times any standard basis vector, pick your favorite one, this will just be the jth column. It's going to rip out the jth column of A. Okay, so this is a very, very nice and important fact to know. It will save you a lot of time in this course. Okay, so if you multiply by the jth standard basis vector, it always extracts the jth column out of A for you. That's the vector you get. Okay, so eigenvalues of diagonal matrices are always on the diagonal. This is actually true more generally. Even if this part was not 0, even if you had something that was upper triangular, let's say, the eigenvalues are still sitting there. Okay, that's just something to keep in mind. Okay, and that's it. So that's the end of this lectures for the first week. This is just a review of linear algebra. Next week we will do, I'll release a set of practice exercises for this week, which will be marked for completion. Next week we'll do an introduction to the principles of quantum mechanics, which are what we'll need to then start talking about quantum computing. Okay, and of course for the principles of quantum mechanics we'll need all this linear algebra stuff, which we reviewed today. All right, so that's it. So if you have any questions, do feel free to go on the Panda discussion group or also email me, of course. All right, that's it. Have a good one. Stay healthy.